people who just really love calculus. All right. So this means plug this in to the f function, right? I mean, if I ask you what's f of 3, you would say, well, take a 3 and plug it in for x, right? So if I ask you what's f of x plus 2, it means put an x plus 2 in for x squared. So one way of working this was you could just work this side, and you could say, okay, I'm going to take x plus 2, I'm going to plug it into here, so that'd be x plus 2 squared, and then minus 1. And now I could FOIL that out, x squared plus 4x plus 4 minus 1, and I get x squared plus 4x plus 3. And you say, oh yeah, g of x is that. Yep, there it is. Okay, completing the square didn't have anything to do with it. Now, so I would not have asked this question this way on a quiz. If I was going to give you this, I just would have said, show that this is equal to this, and let you figure it out however you wanted to, which this would have been the smart way, I think, to do it, with those directions. But then they give you this hint, the kind of complicated thing. The hint, so let's pretend that wasn't there. Okay? Let's pretend that wasn't there. The real question that I think they were wanting you to do with the completing the square was show what kind of a shift or a change from this graph that g is. Now, here's why that's important, because today we're going to be talking about all the different, well, I put it up here. I said our goal today, one of our goals today is memorize these basic functions. Now, we're not going to have to memorize them by Tuesday. They should be memorized, quite honestly. But on the quiz, I'm not going to quiz you to see how well you've memorized them, okay? But we're going to memorize these basic type of functions. Well, one of the basic functions, we'll use the term parent graphs. The parent graph of a parabola is y equals x squared. That's your basic parabola. Now, this is also a parabola, but it's some change in the basic parabola. So my question for you on this one would be, how is this a change from the basic parabola? Well, the problem with writing it like this is you can't tell. You can't see the shift in this. But if you complete the square, you can. So this is why, and this is not going to be a big thing you're going to have to do for the quiz next week, okay? But this is an algebra thing that can be helpful in helping us see these shifts and translations on these graphs. So what we do is this, if you can remember it all from Algebra 2, is completing the square is finding this third piece that would make that a perfect square. I'm going to scoot the plus 3 over there out of the way. Well, what do? How do we complete the square? We take half of the b, this number, and we square it. Half of 4 is 2. 2 squared is 4. So I want to add 4 onto g, but I can't add 4 onto g or I change it. So then I'm going to take away 4. So I really added a 0. So I just added 4 and took away 4. So I really haven't changed g at all, right? So what I have here is still g. It's still this. But now what I can do is I can take those 3 and write that as x plus 2 quantity squared. And the negative 4 plus 3 makes negative 1. So another way of writing g is this. Now look what you got. Can you tell that's a parabola? Because it's squared. What's a plus 2 mean? Left 2. What's this mean? Down 1. So by rewriting this, by using an algebra technique, I can rewrite this parabola into this, and I can tell exactly what that graph is. Now, we have a nice $150 machine that I could have just graphed the dumb thing and saw that it was that as well. And sometimes you'll get to do that, okay? But it would be nice to understand this process. Now, does that come up very often? Not very often, okay? But it is good to go back and look at that and see that we, that we can do this, and this is how we can see a shift in that particular thing. Okay? So that's a little bit about number 60. Okay, what else do you want to see on the homework? 55. Was that the one with the graphs and the volume of the bowl? Okay, now, I did not give you this information. You kind of need it for part B. A sphere volume is this. Normally, I would give you that. Now, if I was really mean, I would say, hey, you took geometry, you should know that. But I understand. Probably don't remember. That's the volume of a sphere. Now, what we have is a half of a sphere here, okay, that's got a radius of 10. And they tell us, but what this problem is really about is about function and function language. So they say that V is the volume in terms of depth, D. So what that means is you have the volume V of D. Okay? Volume's your output, depth is your input. So then they ask you, what's V of 0? Now they have no equation to plug into. That is not the equation. That's the equation for a full sphere. Since we have half of a sphere, I'm actually going to change that 4 to a 2. Okay? And that would be half of a sphere. But that's not the volume equation in terms of depth. That's the volume in terms of the radius of the bowl. The radius is 10. Okay? But we don't know, we can't plug a 1 into here. If I had 1 inch of depth here, I can't plug a 1 into there and get that, because that doesn't mean that we would have a radius here of 1. That's not what that's saying. That 1 there is not a radius. Okay? So I couldn't plug a 1 in or a 2 in and those kind of things. So anyway, V of 0 is saying what? Asking you what? When the depth is 0, D is the input. When the depth is 0, what's the volume? Well, that's easy. We don't have anything to plug into. We don't need anything. We got that. V of 10. When the depth is 10, what's the volume? But this would be the radius, right? This would actually be the radius. So when they say V of 10, that means this is full. Yeah, it's full. Well, now we can use this formula, right? When it's full. Anywhere in between, we could not use that formula. Okay? Because this does not, this piece down here, that would not be a sphere. Or a, right? That would not, if that was 1 inch deep, that would not give you also a radius of 1. Okay? So, volume is 10. We can plug that in, 10 cubes 1,000, so that would be 2,000 pi over 3. On the quiz, I would give you an equation like that if you need it. Okay, and then the last part is which graph is which there. Which graph goes with this situation? A, B, C, or D? It is C. Why not A? Why? Right. So in other words, the graph needs to start at 0, right? It needs to start at 0 because if you have 0 depth, you have 0 volume. So that can't work. Why? Now here's the next thing. So all 3 of those now have an increasing look to them. One is a line, and the one is, what's the term for this? We learned yesterday? Concave up, concave down. Why is it this one? Okay, so the graph we're talking about is volume versus depth. So 1 inch of depth will have a certain volume. The 2nd inch of depth, we will gain more water. There'll be more water in the 2nd inch of depth than in the 1st inch of depth. And there'll be more water in the 3rd inch of depth. So as we plot those volumes, they're increasing. What we say is increasing at an increasing rate. Notice all 3 of those other graphs are increasing. Increasing at an increasing rate, increasing at a decreasing rate, and increasing at a constant rate. If you were filling up something that looked like this, now you would have that situation. Because 1 inch of depth would give you a certain volume, the 2nd inch of depth would give you less volume, the 3rd inch less volume. You're still gaining volume, so your graph's still going up, but it's not growing as fast. That's one of the things we'll do work a lot with, is this idea of concave up, concave down. All those graphs are increasing, but at different rates. So we're talking about increasing rates and decreasing rates. Okay. Anything else? Anything else? I did want to talk about the periodic ones. Periodic. They told you that, was it P? What was that one with the P at negative 30 or, I can't remember what the T or, what problem was that? Number 23, I think. 23?
Yeah.
Is that the one? What was that function called? T. Okay. So they told you that T of, well, the first one, just the real easy one. They tell you the period is 7. T of 0 is 3, so then they ask you, what's T of 7? 3. Because, and again, think of this as a graph. Here's big T is your output. At 0, we get 3. So at 7, we should get 3. And at 14, we should get 3. And at 21, we should get 3. And on and on and on. And go in both directions. But then they ask you this, which is a little different than what I had asked you the other day. Are these two equal? Why? Bingo. The key is those two terms right there. Now, do we know what they are? We have no idea, right? We have no idea what these values are, but it doesn't matter. There's 7, and this is what you would say because you have to explain it. You would say because their inputs, their x values, right? Their x values are 70 apart. That's 10 periods. 10 periods. So they have to have the same output. We just don't know what that output is. Okay? So I would say these are easier. This is a pretty easy question on period. But then something like this, you got to think about a little more. All right? And so expect some questions like that kind of thing when it comes to periodic. All right, I can't think of anything else unless you got something. Any others? We will have some work time today, so if there were some that you were still puzzled on, be sure and ask me, okay? When we have some work time. Okay, so let's go ahead and get your notes out, and let's move on to the last section we have to talk about, at least as it deals with our quiz next week. Which is section 3, so we're looking at about page 24, I think. I believe that's right. Yeah, page 24. All right, yesterday we were talking about the course description over here, and one of the things that is in the course description is it says students should have completed 4-year secondary math designed for college-bound students where they study algebra, geometry, trig, analytic geometry, and elementary functions. So the title of this section is a field guide to elementary functions. On the board I call it basic functions, kind of the same thing. These functions include linear, polynomial, rational, exponential, logarithmic, trig, inverse trig, and piecewise defined functions. So calculus is all about the behavior of functions. And so these are the basic functions we will work with. So you need to be very familiar with them. And the more you know about them, domain, range, are they even, are they odd, are they periodic, those kind of things, the easier you will be able to handle the calculus when we act upon those functions. All right? So we need to kind of memorize some of these basic graphs and what's happening with them. So part of our quiz on Tuesday is this function notation and how it affects these different graphs, okay? It's not a memorization thing like on the quiz. Anytime, if I give you an exponential or a trig function or something like that, you'll be able to use your calculator to graph it if you don't know what it looks like. But the time for that is short. As we go forward, it's going to be assumed that if we're dealing with one of these basic functions, that it could show up in a no calculator situation and you will have an idea of what it looks like. And I'll give you an example of something where that may come up later on down the road. Piecewise defined, we've talked about. That is going to be on the quiz, and we've already talked about how to work out those. Inverse trig, we won't really worry about for right now. Trig, we're going to get into a little bit, not a lot. Monday, we will review some trig, but you're not going to have that stuff memorized for the quiz. You'll be able to use your calculator. Log and exponential, we've done quite a bit of work on. We want to talk about the graphs specifically today, and then we'll hit on rational and polynomial here. Okay, so that's what we're looking at. So let's start with polynomial. A polynomial function. All right, a polynomial function is a kind you're most used to working with up through algebra 1 into algebra 2. Start with the most basic polynomial, which would be a linear. Okay, your old y equals mx plus b kind of thing. All right. The basic parent graph for a linear function is y equals x. I actually shouldn't even put y equals mx plus b, to be honest with you. I should just put y equals x. Now, we use the term parent graph, right? And then we can do all this shifting and stretching and stuff around that. Now, kind of an interesting side note here about linear functions that you probably never have thought of, but in context today of shifting and stretching and stuff like that, think about this picture right here. Think about this graph right here. Y equals, don't write this down. That's your old point slope form, right? Now, if we were going to graph that, we might go ahead and distribute that. And so this would be the graph 2x minus 1. Now, if I was going to graph that, okay, 1, 2, 3, 4, 5. Okay, I would go down here to -1. I would go up 2 over 1, up 2 over 1. And I would have, oh, God, all right, I would have this line right here. Okay, now, the parent graph, though, of lines is y equals x, right? Which would be this line right here, which would be this red line. Now, let's think about this a minute. The red line is our basic line graph. What does this say we're doing to it? Right. The -1 means we go right 1. So this red dot would be moved to here. +1, up 1. Oh, there it is. What's a 2 do? Vertical stretch. Isn't that what's happening? So this point that was here, that's there. Now this point that was here is now up. Not very well done. But it's a stretch of 2. Now instead of over 1, up 1, it's over 1, up 2. Right? So that shows we never thought of lines that way. We never thought of lines as shifting and stretching and stuff like that. But it is. That's what it is. Okay? Now we still probably wouldn't think of it that way because it's easier to just work at it this way and use point and slope. But it is an example of that same thing. Okay, back to this. So we got linear. We've got quadratic. Those are polynomials. All polynomials have nice numbers for powers. There are no negative powers. There are no decimal or fractional powers. Of course, we know our basic quadratic, our parent quadratic graph is y equals x squared. Looks like this. Okay? We also know it could shift and go down, right? If you put a negative on the outside, a negative leading coefficient could flip down, that kind of thing. You could get skinnier and so forth, but we know what a quadratic looks like, hopefully. A cubic, now we start getting into ones that we're not quite as familiar with because we spend most of Algebra 1 and Algebra 2 working with linear and quadratics, right? And then all of a sudden we rush through all these other functions, so we're not nearly as familiar or comfortable with them. But a cubic, I was showing you that the other day, kind of comes up like so, and then kind of goes through the origin, kind of flat, and then gets steep again, kind of an S kind of shape. But a cubic can have humps in it, like a peak and a valley. We, of course, call that a local max and a local min now, right? Now, what happens if it's a negative leading coefficient? The tails go opposite, right? But the thing is, when you have a cubic, the tails go opposite as opposed to a quadratic where the tails go the same direction. And, of course, we realize that whenever we have an even degree, x to the 4th, x to the 6th, x to the 8th, etc., those are going to have tails going the same direction. Now, you can get multiple humps and bumps, though. Now, how many depends on the degree. If you have an x, this could not be an x to the 4th. This would have to be an x to the 6th. X to the 6th, it can always have one less local max min than the degree. So here I've got 1, 2, 3, 4, 5. That would have to be an x to the 6th or higher, right? So an x squared only has 1. An x cubed could have 2, but it might not have any, right? It might be stretched out like this, okay? And an x to the 6th might look like an x squared. It might not have that many, but you always know the tails are going the same direction, and of course it can be flipped and they could go down. All right, an odd power, x to the 5th, x to the 7th, x to the 9th, etc. Those are always going to have tails going the opposite direction, and they could have multiple, right? Could have multiple peaks and valleys depending on how high the power is. Now, the reason this is important is even if you're using your calculator to draw a graph, if we have a question where there's a calculator and you can use it. Remember that degree problem with the door swinging open and we drew that graph very second day, whatever? It wouldn't fit on the window. We couldn't see the graph. We had to go in and change the window. Well, if you don't know, if you draw a graph and it's not there, well, it's because your window's wrong. And if you don't understand the basic shapes of that graph, you're probably not going to be able to set the window. You're never going to know if you're really looking at the graph you're supposed to be looking at. And on a quiz, well, on a quiz, you'll find out I'm not helping you anyway. Very few questions will get answered on a quiz. I mean, if I can't read something or something, that's it. But it's kind of like the AP test or the ACT. You're not asking questions I'm not going to be answering them. So you come up and you say, I graphed this, but there's no graph. Now, I might say, check your window, and then I would say to everybody, hey, everybody, check your window and your graph. But I may not either. I may say, well, it should be there, right? So, I mean, you can ask. I guess what I usually tell people is on a quiz, you can ask me a question, but 99% of the time you'll be disappointed in my answer, okay? But that's what you got to be able to do. You've got to be able to use your calculator and use your graph. All right. So that's polynomial functions. Next one, rational. Rational functions is one polynomial divided by another, but it's not a polynomial. Okay, it's one polynomial divided by another. So an example might be this: x squared plus 1 over x, let's do x minus 2. That would be an example. Now we're not going to get into these very much. Excuse me, we're going to do stuff with these in chapter 2 and chapter 4. But these are the kind of functions that might look something like this. I don't know, not this one necessarily. But they have, say, a vertical asymptote. So it might come in and do something like this. And it might, go up like this or something. It'd be a vertical asymptote there. It could be a horizontal asymptote here. So rational functions, about all you need to worry about with those right now is rational functions very often have horizontal and vertical asymptotes. So they got some strange things going on. And we get into factoring and canceling and stuff, and we're going to deal with those later on. But that's kind of what happens with rational functions. It's a polynomial divided by another polynomial. Okay? All right, so that takes us to page 26. Okay, next page talks about exponential functions. So I think I've got some pictures here that are better than what I could draw. All right, here are some exponential functions. Now, exponential functions have an x in the exponent and a positive base. You cannot have a negative base in an exponential, okay? You would never have negative 2 to the x power because you can't, that raises all kinds of domain issues. Negative 2 to the x power, try to put a 1/2 into that. What's negative 2 to the 1/2 power? That's square root of a negative. You can't do it, right? So an exponential function is always a positive base raised to an x. All right? So you've got these examples here. E to the x is the one we use most of the time. 2 to the x, 4 to the x, you change that base. It just kind of changes how steep it is. 1 to the x, of course, 1 to anything is just 1, so that'd just be a horizontal line. And then if you go below 2, go below 1, like half or third or fourth or something like that, you get this. Think of it like exponential growth versus exponential decay. If you have numbers bigger than 1 in the base, you're going to have this growth kind of shape. If you have numbers under 1, between 1 and 0, you're going to have this exponential decay kind of a situation. But notice they all go through 0, 1. All right, so that's a pretty important part, unless it's been shifted, of course. If you take an exponential and shift it up or move it around, then you're going to have obviously something else, but going through that 0, 1. Okay? All right. Also, notice that this graph here is just a horizontal shift of this graph over here. Or not shift, but flip. Those are just horizontal flips of one another. Now, the reason for that is if you take 2 to the x, think about it now, you don't have to write this down, but if you take 2 to the negative x, what happens when you put a negative on the inside? Horizontal flip, right? Well, if you do 2 to the negative x, that's the same as 2 to the negative 1 to the x power. Because power on power, you multiply the power. And 2 to the negative 1 is 1/2. So 2 to the negative x is the same as 1/2 to the x. So you can see why those two are a horizontal flip of one another. All right, but anyway, that's the graph of an exponential. It's got a horizontal asymptote down here. So it comes down here and it just never touches, goes out forever, right? Now, what's the domain of this? The domain. All real, right? Because that's the x value. So you can put in x, you get x values way out here, you got x values all the way out here, out to infinity, negative infinity to infinity. But the range, 0 to infinity, right? Greater than 0, doesn't ever hit 0 though. Don't include 0. No, the domain can be negative. Remember, that's what you can put in for the x. The base can't be negative. Right, and that's kind of why I said that, because I didn't want to confuse you there. The base can't ever be negative, right, for an exponential. But for an exponential function like this, the x values you can plug in are anything. Anything. Okay, now that's a lot of what your homework's going to be today. Your homework's going to be about, and I'm going to talk about it more in a minute, but it's going to be all these different types of functions. And it's going to ask you those kinds of questions. Domain, range, those kind of things that we talked about yesterday in that. But let's get through the rest of this. All right, so that's exponential functions. Then we have log. This is probably the one we have to work the hardest on memorizing. We probably have a pretty good feel what an exponential function looks like, I hope. We should be really good with quadratics, parabolas, maybe even cubics. Trig, sine, and cosine should be reasonably good at. But this graph is not one we have a lot of expertise with, it seems like, from year to year. So we've got to really work at this. Now, log base e, of course, is just natural log. You notice these are just inverses of the exponential. So instead of going through 0, 1, they go through 1, 0. Instead of a horizontal asymptote, there's a vertical asymptote right here. So this goes down forever and ever, comes up through here. Now, just like inverses, when you switch the x and y, we'll talk more about inverses later on too. But when you switch the x and y, notice the domain and range switch here. The domain is all positives, right? Greater than 0 are your domain values. Your range values are all real, because it goes down to negative infinity and it goes up, and it levels off, but it never gets completely level. It's always going just a little bit up, but very slowly. Now, I wanted to give you an example here for later in the year. I want to show you why it's important to have a basic memorization of the natural log graph. There's a problem, or there will be problems that will look like this. They'll give you a function. This will be a no calculator problem. They'll give you a function that looks something like this right here. And there'll be a bunch of calculus you have to do to it, okay? So you'll do this calculus, which we won't get into right now, but you'll do this calculus to it. And basically the gist of the question will be this. You'll need to know when this is negative. In other words, when the y values are negative. To answer the question, after you do the calculus, you'll basically have to know when that function is negative without a calculus. Well, the best way to do that is a graph. So you would say to yourself, self, what's the natural log graph look like? Well, it goes through 1, 0, and it goes here. But what's that minus 2 do? 2 to the right. So now instead of going through 1, 0, it goes through 3, 0. And instead of having a vertical asymptote here at the y-axis, it's where? It's at 2. And so that natural log graph is going to come up through here, and it's going to do this. And since I know that about natural log, and I know that that's a shift of the 2, and all I need to know is when are the y values negative, what would you say? let's use our interval notation. From what to what? From 2 to 3, right? In the interval 2 to 3, this graph, this function is negative. In the interval 2 to 3, when x is between 2 and 3, right there, these y values are negative. And you've answered the question. But without that knowledge, really without knowing the basic graph shape and the fact that that's shifted 2 to the right, that becomes a very hard question. You've done all this calculus and then you can't answer the basic question you need to. So understanding and remembering these basic graph shapes is important as we go through the year. All right, so that's the log. The next one was a trig. We're not going to worry about the here about the trig functions to speak of right now, other than just know your basic sine and cosine shape. It also gives you the tangent graph. So if there's a question on the homework that asks about the tangent graph, just look back on page, I think it's 29. No, it's 33. I'm 32. On 32, they give you a basic. They give you a picture of a basic tangent graph, a basic cotangent, and those. Most of the time on the quiz, you'll be able to type that into your calculator if you need to look at it. On the homework, you can if you want to too. All right. So I'm going to just summarize here real quick, and then I'm going to let you have a fair amount of work time today on your homework. So where we're at, I've pretty much given you all the new information I'm going to give you for Tuesday's quiz at this point. Okay. Monday will be about going over the homework and seeing what questions you have, summarizing one more time what's going to be on the quiz, and then we're going to spend some time doing more trig stuff. Not stuff necessarily to be on the quiz, but just spending some time with some trig review. So where have we been? Section 1.1 was just introducing us to function notation, telling you that functions can be equations, they can be graphs, they can be tables, they can be words. You have to be able to interpret a graph if I give you the context of it and understand the function notation. Section 2 was about graph language. Increasing, decreasing, concave up, concave down, local max, local min, roots, intercepts, domain, range, even and odd functions and their symmetry that they have, periodic functions, all of that language. Now section 3 is introducing you to all the different types of functions we will deal with. Your homework today in section 3 then is going to be asking you the language you learned in sections 1 and 2 and apply it to these various functions. So they're going to ask you about the exponential function and ask you for its domain and its range and where does it concave up and does it have local max and mins and does it do this and does it do that. Okay? So your homework is going to be the 1.3 homework questions. There's one of the problems here, number 7, before we get started, that in part F, don't you love it when you get the homework problems and you say, well, that's not that many, and then you see